Okay, 10.3. We're still just sort of basically dealing with um, simple probabilities. We're talking about a random outcome, and we'll just define random outcome real quick. Random outcome is an outcome in which the result in a trial is not affected by the result of a previous trial. So why don't you go ahead and copy that down real quick. An outcome in which the result in a trial is not affected by the result of the previous trial. These are also sometimes referred to as independent events. Because they do not depend on anything that happened before or that will happen after. If you think about tossing a coin, if you toss a coin, you're going to get a head or a tail, okay, with your first toss. That second toss, if you toss it again, it doesn't matter if you got a head or a tail the first time. It doesn't matter if you got a head, you're not more likely to get a head or a tail the second time. The second toss does not depend on the first one. Hypothetically, you could flip a head here and a head here. Now, you're more likely to get a head and a tail, right, because it's 50-50. But, you know, if you get a head here, it doesn't matter. You're still 50-50 on if you'll get a head or a tail here. Just kind of like a little quick sidebar. This is often what's referred to as the gambler's fallacy. If you are playing a game and if you're on a roulette wheel or something and the number 6 comes up 3 times in a row, that doesn't make it more likely that it will come up the 4th time. Okay, if you get a 6 3 times in a row, that just means that something weird happened that is out of the ordinary. Okay, but it doesn't make it more likely that, if you say like, oh, there are 3 6s in a row, I'm going to put all my money on 6 because it's, 6 is coming up a ton right now. That doesn't make sense, and that's why it's the gambler's fallacy, is because if you see that and you think, well, I'm going to put all my money on 6 now because 6 is happening all the time, you're probably going to lose all your money because 6 is not more likely. It's just as likely as it was before. It just happened to be spun 3 times in a row. Okay, so we'll look at example A. Mario is an entomologist who studies the behavior of bees. He videotapes bees leaving a hive, counts 247 flying east, 628 flying west. So if we're going to find out the experimental probability of a bee chosen at random to fly east, we first need to figure out the total number of bees. So 247 plus 628, total number of bees is 875 bees. So if we're looking for the probability of one flying east, that'd be 247 divided by our total 875, which is about 28%, or about 0.28. If we're looking for 628 out of the 875, and we'll just round. We know that this has to add up to 100%, so we can just say that that's about 0.72. So about 28% of the bees chose to fly east, and about 72% chose to fly west. 28 out of the 100 will fly east. And that means that 72 of the 100 will fly west. Okay, so pretty simple probabilities. Just keep in mind that they are independent events. They're random outcomes. So it really doesn't matter what happened in a previous trial or in a future trial. That's not going to affect what's going to happen in the current trial. So before class, Ms. Olson's algebra class last year had 20 students. 4 of them consistently blurted out in class, while 16 raised their hands. This year, Ms. Olson has 50 algebra students. Using last year's data, how many blurters does she have this year?